you can't have two-way communication because light isn't infinitely fast. I mean, it's so interesting. All right. Okay. Ellipses. Why do we care about ellipses? That was a great question. The reason we care about ellipses is because when Copernicus said things are revolving around the sun, people were like, man, that was really interesting. And then in Denmark, there's a guy, and his name was Tycho Brahe, and he was very famous. And he was a very famous, like, naked eye astronomer, because telescopes weren't readily available at the time. And so he would just look up in the sky and be like, oh, this is where this thing is, and this is where this thing is. And every night, the position of the stars changes by about 4 minutes. And they knew about this. They had a good sense of it. And that's how they knew that a year was 365 and some fraction of days. But there was a young German mathematician who was really interested in the sky, and his name was Johannes Kepler. And he went to work for Tycho Brahe, who was, he liked court life, right? And he didn't like this upstart coming in and trying to take over. And so he told Kepler, like, listen, if you want to go work with this data, you go work with this data. If you ever figure anything out, you come back and let us know. Not thinking that Kepler was ever going to figure anything out from all this, like, where are the planets every night data. And then a couple years later, Kepler comes back, he's like, all right, I'm done. And they're like, what do you mean you're done? He's like, I figured it all out. They didn't know there was anything to figure out, let alone that he was going to actually figure things out. And what he figured out was that the planets do not go around in circles. They actually go around in ellipses. Now, as we talked about yesterday, a circle is an ellipse. You just take the both focal points and put them on top of one another, right? But the point is that if you look at an extreme view, okay, let's say, oh my God, it is so much harder to draw them than you would think. Ooh, that's a good one. If you look at an extreme view, like a comet, for example, all planets and comets, anything in the solar system, orbit the sun in an ellipse where the sun is at one focal point. That's what he found out. Everything orbits with the sun at one focal point. Question always asked, like, what's at the other focal point? Literally nothing. There's nothing out there. And what's cool about this is that now if you look at the planet, here, for example, it's moving fast. And over here, it's moving slow. The closer you are, the faster you're going. The farther away you are, the slower you're going. Yeah?
So is he correct? So is it like that? Like the sun is in one focal point and it just goes around like that?
Mm-hmm. So every object has its own ellipse, right? Not everything is the same focal point, because every object has its own orbit. But yeah, it is 100% that the sun is at the focal point for every object in the solar system. Now, this is more like what a comet would look like. Okay? The Earth is almost perfectly circular, and the reason you know it's almost perfectly circular for the Earth is that if it looked like this, the seasons would be all jacked up. But our seasons last for 3 months apiece, right? So here the seasons would be different, not because the distance is different, because of the whole tilt problem. But yeah, they're almost nearly circular. The planets are almost nearly circular. They're just offset a little bit, just a little bit. But comets are big time like this. So think about something like the most famous comet of all time is called Halley's Comet. You guys ever heard of Halley's Comet? It takes 75 years for Halley's Comet to come back. Does that make sense? So in this picture, like the Earth orbit is like here. That'd be like the Earth orbit. So it comes in and it comes inside, and we can see it when it's close to the Earth orbit, true? But it's moving fast when it's close to the Earth orbit, and then as it gets far away, it slows down. So it spends, you know, basically 74.5 years out here where we can't see it, and then when it gets close, it's moving really fast, slingshots around, and then slows down out here, and then slingshots around, and then slows down. Yeah.
So like every planet or like comet or whatever just moves in a different circle like length around the sun?
Yes, everything that revolves around the sun does so in its own ellipse,
Yeah.
and they're all different from each other. Yeah.
Would they ever collide?
So they're not on the same plane. Like, they're like this, and then the Halley's Comet like comes in like this. So I don't think it intersects any orbits, because they're not on the same plane. Yeah.
So your comet, it's separate from the belt. It's like its own, object. And is it farther, as far as the pathing, is it farther out past like the first belt?
So some are, some aren't. There's, I mean, so many comets, right? But they're doing their own thing. They are not belt objects. They are comets. See if they can do it.
There was a comet that hit Jupiter though in the 90s.
Oh, Shoemaker Levy?
Yeah.
Shoemaker Levy 9? Named after Mr. 9? You'd like stop that down. Just please stop.
No, it's fine, it's Friday.
It's Friday. Oh. So this is cool. Oh, you guys can't now. Marky, can you shut the lights off, please? So this is a very cool thing. Okay, even that last one. Even that last one. Can't see a thing in there. Ah, much better. So you can see like Saturn, here's Uranus, here's Neptune down here. I'll zoom in here so we can see the inside one. Okay, and so we're seeing here, here's the sun, Mercury, Venus, I don't know what that is. It's probably like a space probe that they launch at something. Earth, here's Venus, and then here's Mars out here. And then you can see Ceres is all the way out here in the asteroid belt, as is Vesta. Okay, so I'm going to go out now. And there's more, like Tempe 1 and Psyche and Wild 2. All right, now Jupiter's out here. So you can see this. You see how this orbit here, it looks like it's coming from somewhere else? That's got to be a comet because it's not going in a circular orbit. Okay, there's Jupiter. There's Uranus and Saturn and Neptune. Oh, look at, here's Haumea and Makemake. Here's Pluto up here. Now, I'm going to click and drag and it's going to tilt the whole thing. And one of the things you can see here is you see how Pluto's orbit is off the axis? The fact that Pluto's orbit is off the axis is one of the reasons we knew it's not one of the 8 major planets. Because it doesn't do what the rest do. It's doing something else completely. So that's how we know it's a trans-Neptunian object. Neptune. Oh, look at this Comet.
So the ones that are farther, like, out from the sun, from Earth, have, like, longer Earth years?
Yeah, so the farther out you go, the longer it takes you to go around. So anything farther out than the sun, or farther out than the Earth, will take more than a year to go around. Oh, the Voyager 1. That thing, you know that thing's hella far away. Ooh, this is fun. Get my merchandise, and download the app.
Did you just run
You know a lot of random stuff, Don. I know. It's got music too. Okay, that is more than enough of that.
This is fun.
No, I don't want the night sky. I want the night sky to go away. Planets show, moons show, dwarf planets show, comets, oh, show. Spacecraft? No. Stars? No. So this is 100. So this is cool. So this is the 100 AU bubble out here. Okay. Look at Eris. You can see Eris here has a very, like if it looked at, you see how it's very elliptical in its orbit there? So here's Halley's Comet. Can you guys see this here? Oh, look, it's like way out here. And it's going to come in and then go back out. It's like, what is this? Ooh, there's a Comet 67P. Look at this thing. Nice ellipse. Okay. Here's Ceres. You can see the asteroid belt here. Is that cool? You guys have a sense of what we're seeing here? And then this out here, you can see the Kuiper belt is out here. Does that make sense? And if we go and look on the plane again, what do we notice about, here's Halley's Comet. See how it's off the axis? Comet and Makemake are also off the axis, which is cool. All right.
How am I like an 18-year-old and never seen this before?
Why are galaxies flat? That's a great question. Why are galaxies flat?
Our sun and the Earth, and all the planets and moons and dwarf planets and asteroids and comets, the solar system in short, formed about 4.6 billion years ago from a nebulous cloud of swirling gas and dust, which coalesced thanks to the irresistibly attractive force of gravity. However, this nebula started off more or less as a big shapeless blob. So how did our solar system end up with all the planets and their moons orbiting in a flat disk? I mean, we've all seen the planetary model of the atom, which is definitely wrong when applied to atoms, but it also kind of suggests that planets might revolve around the sun every
It's definitely wrong when it
So
comes
is
to
our solar
planets,
system
too.
somehow special in its flatness? Or is the planetary model of the atom doubly wrong? Well, our solar system definitely isn't alone. Many exoplanet star systems are flat, a lot of galaxies are flat, black hole accretion disks are flat, Saturn's rings are flat, etc. So why, when there's all of 3D space to fill, does the universe have this preference for flatness? The answer has to do with two things: collisions and the fact that we live in 3 dimensions. Bear with me. Anytime a bunch of objects held together by gravity are zooming and circling around, their individual paths are nearly impossible to predict, and yet collected together they have a single total amount that they spin about their center of mass. It may be hard to figure out exactly what direction that rotation is in, but the mathematics implies there must be some plane in which the cloud, taken as a whole, spins. Now, in 2 dimensions, a cloud of particles rotating in a plane is flat by definition. It's in 2 dimensions. But in 3 dimensions, even though the rotation of the cloud is given by one plane, particles can whiz around far up and down from that plane. As the particles bump into each other, all the up and down motion tends to cancel out, its energy lost in crashing and clumping. Yet the whole mass must continue spinning inexorably, because in our universe, the total amount of spinning in an isolated system is the same. So over time, through collisions and crashes, the cloud loses its loft and flattens into a spinning, roughly 2-dimensional thing, like a solar system or a smaller galaxy.
I love the fact that the conservation of angular momentum. Like, how another day wasted by me ranting.